Hey guys, today should be hopefully the last. I know the last couple of videos have been kind of long. Today should be the last in that kind of string. And they are long because, again, we are really trying to bring a lot of different ideas together, a lot of topics together, and kind of this is sort of the basis of really everything that we'll be doing is especially for this unit, next unit, is the equation we discussed in the last video and that we're going to derive today. So, here we are. We're going to derive an equation. Move myself up here so I'm kind of out of the way. We're going to derive an equation for the displacement. So equation which will tell us displacement, which is how far an object moves, for an object that's accelerating. Remember, we already know for an object that's not accelerating, to find its displacement or the distance it's traveled is quite simple. We just take its speed or its velocity and multiply by the time. But what about when an object is accelerating? Well, that's what we have here in this scenario, right? Because this is a velocity versus time graph. So you can see that this object at point A is moving, sorry, you can't see my cursor very well, but at point A, its velocity is, we don't know, there's no number, but it's less than what it is at point B. So that's an acceleration because it's a change in velocity. Now this is a positive acceleration, but it could just as easily be a negative acceleration. It's not going to make much of a difference. Well, what we discovered last time, sort of one of the big takeaways, is that if we have a velocity versus time graph, the displacement is the area underneath that graph. So if I would like to know what is the displacement between points A and B here, I'm really asking what is the area under the graph, and I can't draw straight lines very well, sorry. I used to have a pen or a little tool that would help me, but I don't have that, so they're going to be crooked lines. So anyways, we're asking when I say what is this displacement, I'm really asking, another coded way to say that is, what is the area of this right here? What is the area of this figure? And that's a strange one, right? Kind of looks sort of like a irregular pentagon, I guess, as 1, 2, 3, 4. No, it's a quadrilateral. So maybe some kind of trapezoid or something. You might say, well, I don't know how to calculate the area of this object. And I would agree, I don't know how to calculate the area of this object. But I can quickly change this into two objects that I can calculate the area of, right? If I just draw this line here, so again, it's supposed to be in line with that line right there. Right? Then I have two very easy, simple shapes, right? I have a triangle and I have a rectangle. Just as a quick reminder, if you forgot, the area for a triangle is 1/2 base times height. The area for a rectangle is just length times width. So if I take these areas, and you can add areas together, so if I find the area of this rectangle, plus the area of this triangle, I will have the total area, which is the total displacement. But here's what I'm going to try to do. I'm going to try to represent that without using numbers. I'm going to try to get a general equation here and see if I can figure out, what these are. So we need to figure out these sides, right? We need to lay one. Actually, notice that the base of this triangle and the width are going to be the same, right? And this side right here is going to be the same. So that's going to be an important side. So let's figure out what we're going to name this. For now, let's just name this side from here to here. It would be T2 minus T1, right? So if this is like this point right here, right? If I was going to label this point, maybe I'll just call it T2 x comma the y value is, let's just say, vi, because this is a velocity, right, on the y-axis, and that's the initial velocity. This point right here would be T1. In fact, let me just change it to make it this same. I'm going to TF and TI. So this point would be TI, that's the x value. The y value would be the same, it's the VI. Okay, so this, let's just go ahead and label this point 2. So this point here has the same x value, right? So this would be TF, comma, let's just call it VF is the y value. Okay. So now we can label our sides, and bear with me. I know it'll get a little ugly, but it'll be nice at the end. So this length right here, right, for the rectangle and the base of the triangle, is going to be TF minus TI. Now, if you'll permit me, I'm going to use delta notation, and I'm going to call this delta T. Again, that means the exact same thing. So rectangle, okay, let's do the rectangle right here. The area of the rectangle is going to be the length times the width. So let's get the length. The length goes from what? 0, this is obviously 0 down here, to VI. So the length, so this side would be VI minus 0, which is of course just VI. So this length is just going to be the initial velocity. So the area of the rectangle is going to be VI plus, or excuse me, times, wrong, length times width, VI times this width we just described is, sorry, I lost my cursor, delta T. VI times delta T. Great. I'm going to come over here, maybe I'll do a different color so it stands out a little better. I'm going to do the area of the triangle is 1/2. The base is still delta T times the height. Now what is the height here? The height is VF minus VI. I could call that delta V. I'm not going to for a specific reason, but I'm just going to leave it as VF minus VI. So then the total area is simply going to be, which again the total area in this case is the displacement, is going to be VI times delta T plus 1/2 delta T times VF minus VI. Now there is a way we can, this is an equation you could use. There's another form of this equation that we can use though, because notice that we have some similar, if I were to distribute this, right, notice we'd have almost the exact same thing here, right? We'd have VI delta T, there'd be a 1/2 there, and there would be this 1/2 delta T there. So I'm going to, actually I'm probably going to pause real fast and get some more space so I can write this out. Okay, so I moved things over, and now you can see hopefully a little bit better. And I tried to rewrite what we have so far. So we have that the total area is going to be equal to the initial velocity times delta T plus 1/2 delta T times VF minus VI. Now I want to make one quick substitution here that'll make, and this is perfectly fine. This equation is correct. You could use this equation to solve problems if you want to. There's a way I think makes it a little bit more clear. It's a little bit easier, and that's what I'm going to show you now. So you may remember, hopefully, from our, I think it was last video, we had this equation. The final velocity was the initial velocity plus the acceleration times the time. Now really when we say time, we get kind of sloppy. Really it's delta T, the change in time. This is the final velocity. This is how you calculate velocity for accelerating object. So what I'm going to do is I'm going to take this VF, well, this equation for VF, and substitute it right there. And like I said, it's going to look kind of nasty, but then it'll actually work out really well. You'll see in a second. So let me rewrite it all over. Maybe this time I'll use green. I'm going to try to, I'll need a little bit more space. So the total area here is going to be, I want to make sure you're clear this is area, not acceleration, is going to be VI times delta T, that's not going to change, plus 1/2 delta T times, okay, instead of writing VF, I'm writing VI plus a acceleration delta t minus vi. So again, all I did was just substitute, literally instead of writing vf, I wrote this equation there for vf. And look what happens, vi minus vi, those cancel each other out. So then I have at the total area, and really I'm just going to go and write this as the displacement. The total displacement is going to be vi delta t plus 1/2. Now look what happens. I'm going to multiply delta t times a delta t, so delta t times a, so the a is there, and then delta t times delta t is delta t squared. And realistically, we know this is the change in time. A lot of times our initial time is going to be 0, so you could even further write this as the total displacement is going to be the initial velocity times the time plus 1/2 a t squared. And that's the displacement. The only thing this equation doesn't account for is if there was an initial displacement, but you can easily account for that because you can just say plus some initial displacement. And so I know that was kind of a lot of work, but what we have here at the end is worth it, because what we have is this is a general equation. This is an equation that describes the displacement, how far an object travels for any object that is accelerating, as long as the acceleration is constant and not a changing acceleration. And this equation describes the area under this graph. And so that equation, if I clean it, I typed it out here so you can see it a little bit easier, is this right here. So displacement is going to be equal to initial displacement plus the initial velocity times time plus 1/2 a t squared. And that equation is actually pretty simple to use, as you'll see in just a minute, even though the derivation of that equation might have looked a little complex. It's not too bad to use. Real quick, let's just check if this makes sense, right? Because this is actually, even though it may not look exactly like it, this is ax squared plus bx plus c, right? Because it's one term squared, then the term to the first power, and then the term is not there, or the term is to the 0 power. And that, so I mean, it's backwards, right? But this is a quadratic equation, and that makes sense because remember, if we have an object that's just this is the displacement versus time graph. If we have an object that was maybe at rest at the beginning and it was accelerating, its displacement would look like this. Displacement versus time graph would look like this, which is a parabola. And this is a quadratic equation. And that's going to come up a whole lot in our second unit. So you can, again, you may have thought in the past, well, when you're learning about parabolas, why do we learn about parabolas? Like, what's the point? I don't understand. How could you possibly use a parabola? Well, it turns out, whether you like it or not, if we have an object that's accelerating, that displacement, the function of displacement against time, displacement as a function of time, is a quadratic equation. And so if we know how to solve quadratic equations, later on that's going to be able to allow us to figure out when is that object at a specific distance. Okay, let's look at an example problem. I think this is the first one I have for you. What is the displacement of an object after 6 seconds, which moves with an initial velocity of 4 meters per second south, or 4 meters per second, sorry, it's positive 4 meters per second, starting a point of 150 meters south and acceleration at 2.3 meters per second squared. Again, acceleration is a vector, so since that's positive, I'm assuming that's a north, acceleration is north. So again, if you know how to use the equation, this is actually pretty straightforward because we just simply need to take our equation. I'll write it again so you have it. Displacement is the initial displacement plus the initial velocity times the time plus acceleration times the time squared divided by 2. And that's the exact same. Hopefully you know that is the exact same thing as 1/2 at squared, right? It doesn't matter. That's 1/2 times a times t squared is the same thing as a times t squared divided by 2. And the order doesn't matter since we're multiplying. So you can use it interchangeably. All you need to do is identify the pieces that go into this, and if you know units, it's really easy, right? With initial displacement, it's meters. So initial displacement is because it's south is negative 150, plus initial velocity was, I'm looking for meters per second, is positive 4 meters per second. times my time is 6 seconds, plus my acceleration is positive 2.3 times my time is still 6 seconds squared divided by 2. So at this point, it's just calculator work. Hopefully you know how to put this into the calculator. If you don't, I'll be happy to help you. Negative 150 plus, in parentheses, 4 times 6, plus, in parentheses, 2.3 times 6 squared divided by 2, or times 1/2 is the same thing. All right, and for my answer, I get that the displacement after 6 seconds, is one way you can write that, is going to be negative 84.6 meters. So this is some object that's traveling, and after 6 seconds, we know its position is, since it's negative, that's south, so 84.6 meters south. All right, one more example like that. And again, I would encourage you to stop it, see if you can figure this out on your own. It's actually pretty simple, really, using the equation. Deriving the equation may not be as simple, but using the equation is pretty straightforward. So you can pause it and give it a try. I'm going to show you the solution now. So in this case, we have x equals, should be negative 40. Again, just pay attention to your signs, plus velocity of 18 meters per second south, so that's negative 18 times 22. And notice these have to be in seconds. Maybe I should show you that real fast. Okay, let me show you that real fast. It's not that big. Negative 40, let's see what happens with the units. Negative 40 meters plus negative 18 meters per second times 22 seconds plus 1/2. I'll just do the 1/2 out here. A is 2 meters per second squared times the time, which is 22 seconds. I really ran out of room here. Let me just do this last term up here. I'm sorry. 1/2. A acceleration is 2 meters per second squared times 22 seconds. So what happens when I do this right here, right? Sorry, it's 22 seconds squared. So when I do 22 squared, I'll get some big number or whatever. But when I do seconds squared, I'll get, well, obviously seconds squared. So seconds squared, that second square will cancel with this one, and notice that you'll just have meters left over. Right? Likewise, in the second term, meters per second times seconds, the seconds will cancel, you just have meters. So every one of these terms ends up being a displacement, right? This is your initial displacement, right? This second term represents the displacement from your initial velocity. Back to our graph, that would be that rectangle underneath. And then this last term is the displacement due to your acceleration, and that would be the triangle. And again, you see it 1/2 A, base times height, sort of there. All right, so when you put it all together, negative 40 plus negative 18 times 22 plus 0.5 times 2 times 22 squared. All right, and for my final answer, I get positive 48 meters, or you could just say 48 meters north. So again, this object struck ends up at 48 meters north after a total of 22 seconds. Okay, one more example, and again, I know this video is a little long, but there's no other assignment today other than watch the video and take notes. So hopefully you keep up with that. Find the displacement between 2 and 9 seconds. Okay, you have two options here. You can do either one. Pick whichever one you want. But your two options here are as follows. And really, it's the exact same thing. That's really what I'm trying to emphasize here. You could, right? So you could do this graphically, right? What you're trying to find is the area between 2 and 9 seconds. So that's the area of this object here, which would be the area of this rectangle plus the area of that triangle. Let's say that's the way I'm going to do it first, okay? So I'm going to do it that way. So then my displacement is going to be, let's do the triangle first. So the triangle first, well, let's do the rectangle first. So the rectangle will be, what is this length here? It goes from 2 to 9, so this length is 7. If you want to get specific, it's 7 seconds. What is this height? It goes from 0 to 2, so this height here is 2 meters per second. And then the only other thing we need is this right here, right? This height of the triangle. For the triangle, the height, it goes from 2 to 8. Wait, no, I'm mixing my units up. Let me make sure I didn't mess this up. 2 to 9, yeah. Oh, okay, yeah, I see what I did. Again, very human to make mistakes. Just hopefully you recognize when you make a mistake. 4 meters per second is the height here. That's my fault. Okay, because it goes, this is the y coordinate. It goes from 0 to 4. And then this would be from 4 to 8. So this is another 4 meters per second. So obviously I didn't draw this to scale. So actually the same height, but that's a coincidence. Okay, so then my displacement is going to be let's do the rectangle first. So the length is 7 seconds times the height is of that triangle's or the rectangle's 4 meters per second plus, let's do the triangle, 1/2, base is still 7 seconds, times the height is 4 meters per second. Okay, so what I get here is 7 times 4 is 28, plus it's going to be 14, I think. Huh? 28 plus 14, you get a total of 42 meters. So that is our displacement. Well, that's one way you can do it. So again, you can see there, it's hopefully not too hard as long as you remember it's x comma y, which I always struggle with. That's why I usually would have to write it out if I was doing this on paper. X comma y. The other option is you can use the equation, right? We can use this equation here. X equals xi plus vi times t plus a t squared divided by 2. Okay, so what would that be? X equals the initial displacement. We don't know, right? That there's a piece of missing information here. We can't figure out what the initial, we can't figure out where this thing actually began because these are velocities. But that's okay. We'll just call it 0. That's kind of, it doesn't really matter. It's not going to affect. If we just care about what happens between 2 and 9 seconds. So I don't care where it starts. Plus the initial velocity here is again x comma y. Y values or velocities is 4. Times the time, how long is it? It goes from 2 seconds to 9 seconds, so that's 7 seconds. Plus, acceleration. How do I get the acceleration? Remember, the acceleration is going to be the slope of this line right here. So that line, the slope of this line is going to be off to the side here. The acceleration is 8 minus 4 divided by 9 minus 2. Rise over run. So 8 minus 4 is 4, divided by 9 minus 2 is 7. Okay, so the acceleration is 4 over 7 times the time squared, and then it's all divided by 2. All right, so I'm going to put that in my calculator. 0 plus 4 times 7 plus 4 divided by 7, 4/7, times 4 squared divided by 2. And I got a different number. That's not good. All right, I'm going to pause the video and see where I messed up. Sorry, guys. Okay, I see where I went wrong. Hopefully you caught it as well. It's the wrong time, of course. It's the time squared, and we already put in the time once, so I should have already known what it was. It's 7. Okay, so apologies, but if you do 4 times 7 plus 4 divided by 7 times 7 squared divided by 2, I mean, again, you just put all this in your calculator and make sure you put the right numbers in. You get 42 meters. So again, we got the exact same answer both ways, and really we did the same thing. It may look different, but it's the exact same thing. I mean, this equation, remember this equation that we got, came from doing all this, okay, what's the area of this triangle plus the area of the rectangle? Okay, so when you're asked to find the displacement between 2 points on a velocity versus time graph, you can either do it by calculating the area underneath the graph, or you can use the equation that we just discovered. All right, I know it's a long video. Sorry for the mistakes. Hopefully I caught them all. Feel free to let me know if there's one that I didn't catch. And thanks for watching. As always, let me know if you have any questions. Bye.